Hey everybody, welcome back. In the previous segment, we looked at a simple recursive type of natural numbers. And in this segment, we're going to look at a couple of more interesting recursive types. And in particular, I like this type. Remember when we were doing the parser, we were trying to build an abstract syntax tree that represented the structure of our string as a tree. But when we were doing parsers, we didn't know yet how to define new types. So instead, we computed the value of the expression as we were parsing. But with recursive types, we can define an algebraic data type of expressions and then define various interesting functions over those expressions. How would we define expressions in Haskell? Well, again, we define an abstract base class expression and then three concrete subtypes: simple value, multiplication, and addition of expressions. And we can now write that tree on the previous slide as follows. We add 1 to 2 times 3. Okay? Once we have expressions like this, we can define recursive functions over these expressions. And again, they all follow the same structure. We pattern match over each case. You see that here? You don't have to look at the definitions yet, just look at those pattern matches. And then we do something here. Okay? And in this case, when we want to compute the size of an expression, we want to count how many values appear in that expression. Well, if it's a value, it's 1. Otherwise, we recursively calculate the size of the left and the right-hand side and add them up. In an object-oriented language, you would probably make size into a virtual method of the expression superclass and then override that virtual method in each of the concrete subtypes. Here's the evaluator for expressions, or the interpreter. So what it does is it takes an expression and calculates the integer value. If you already have a value, you're done. Otherwise, you evaluate the left-hand side and the right-hand side. And if you happen to have an addition, you add them up. And in case you have a multiplication, you multiply them. When you look at the structure of those functions, what you see is that all they're doing is they're replacing the constructors, respectively value, add, and mul, by other functions. So let's go back here and check that. So in this case, I replace the constructor val by the constant function 1. Here I replace the constructor add by plus and mul by plus. And for the evaluator, we replace this constructor by the identity, add by plus, and the constructor mul by times. And guess what? If we would define a fold R over expressions, then we don't have to write 2 recursive functions. We can do it once. And in that case, for example, the eval function simply reads as follows. We replace val, the val constructor, by the identity. We replace the add constructor by plus, and we replace the multiplication constructor by times. Okay, next example, binary trees. Here's a picture of a binary tree, and we will deal with binary trees that have values in the nodes and values at the leaves. And that leads to the following recursive definition. A tree is either a leaf with an integer, or it's a node with 2 subtrees and an integer right there. And the picture of the previous slide becomes this. We had a node with 5 at the root and 2 subnodes that had a 3 and a 7 respectively, etc. So this value here represents that picture. You see 5, 3, 7, 1, 4, 6, 9, 357 1469. That sounds like a telephone number. Okay, now just like on expressions, we can define recursive functions on the structure of binary trees. So for example, we can search if a given integer is present in this binary tree, and then we will return a Boolean. And we have two cases. If we have a leaf, then we check that the value at the leaf is the same as the value that we're looking for. And that's the result of the Boolean, no recursive invocation. When we have a node, we check whether the value at that node is the one we're looking for, or we check whether the value occurs in the left subtree, or we check whether it appears in the right subtree. Okay? But when the integer does not occur in the tree, we will traverse the whole tree. That's the algorithm there. Now let's look at another function here. Let's try to find it in a different way. So let's first say we take the tree, we flatten it into a list. Okay? So when we have a leaf, we return the singleton list. When we have a tree with a left and a right subtree and a node, we first flatten the left subtree, we splice in that value, and then we append the right subtree. Okay? Now we say that a tree is a search tree if when we flatten it to a list, it is sorted. So our example is a search tree because when we flatten it, we get a sorted list. 1, 3, 4, 5, 6, 7, 9. All right? So now we can define occurs as follows. If we have a search tree, we can check whether it's a leaf. When we have a node, we check whether it's, the values are the same, we return true. Now, since we know more about the structure, we only traverse one path down the tree. So we don't have to say, if it's not the same, we're checking this, or we're checking that. No, we know that if m is less than n, if the number that we're searching for is less than the node here, then we only have to search in the left subtree. If this gentleman here is larger than n, then we only have to search in the right tree. So now we don't have to search the whole tree, because we have exploited the fact that the values in the tree are in a certain relation, and we defined that relation by saying when you flatten the tree, the result is a sorted list. Okay, happy hacking, and see you next week.